And so
Thank you very much. Yeah, so as Marco said, robots are designed for a variety of tasks, and one of the most important ones from my perspective is dangerous environments, because that's where robots are replacing humans in situations where a lot of people get hurt. And the problem is that a lot of routing algorithms for teams of robots don't consider this kind of danger. And so that's the main idea behind the thesis, is that we want to be able to incorporate risk sensitivity, specifically with catastrophic failure of robots, into these routing algorithms. So to give you just a quick video of what the output looks like, what you're looking at here is a team of 20 robots that's trying to do an environmental monitoring mission in a heavy storm. And so the red dots are showing where robots fail. And the reason it's important to take that into account is because if you want to take a particularly important measurement, it's important to know what the probability is that the robot going to do that measurement will actually succeed. And so that's where our routing algorithms come into play. There we go. And there's many applications in robotics where this shows up. So for example, what you're looking at here is a robot that's being developed at the University of Nebraska, and its goal is to help firefighters, specifically the hotshot crews, whose job is to burn away fuel from in front of a big forest fire. And they do this in order to redirect it away from sensitive areas such as housing developments or bigger forests. And the reason why this is a dangerous environment is not just that there's a fire and a lot of gusts, but also in order to aim the fireballs that it's shooting correctly, it needs to be very close to the ground. And this is generally not the way that we want to operate our robots, and so we need new routing algorithms to handle this situation. Another example is where we have this drone whose job is to sense tornadoes and to get more information about how strong they are, where they are, and where they're moving. And again, this is a very dangerous environment because we have huge gusts, and that's generally not where you want to fly your UAVs. And so we need new algorithms to approach this problem. And finally, there's also a search and rescue application. So here what you're looking at is a UAV that they're testing down in Australia to do lifeguarding. And it actually made a successful save a couple weeks ago. And the reason why this is useful is because a lot of times lifeguards are at risk when they go out to save someone. Not only because a drowning person likes to cling on to whoever's saving them, but also because when there's heavy storms or winds or strong currents, then the lifeguard has to work very hard to bring the distressed people home. And so having robots that are able to fly during any weather close to the water will help a lot. So we take these real-world applications and abstract them to several more mathematical situations. So the first problem we look at is this team surviving Orienteers problem. So what you're looking at in this figure are a bunch of locations that we're trying to deliver resources to, and then road networks which connect the locations. And the trick is that each time a robot crosses a road, there's a probability that it fails and won't continue along this mission. And so this introduces that notion of risk that we've been talking about, where there's catastrophic failure that we need to take into account. So our objective is to maximize the expected number of sites that we service while not risking our robots too much. Now, a way of extending this problem is to consider a constrained version where now we have to handle some notions of independence. So we might have limited numbers of each type of robot available, where we have different sensor qualities or resource types that we're delivering. There might also be limited traffic that we can put through a region. So what you're looking at in this figure is an environmental monitoring situation where some regions are more sensitive than others, so we can't send as many robots through them, and some regions have different types of sensing that needs to happen. So if you're going to take measurements about a whale, you need a different UAV or a different UUV than if you're going to take a measurement about a coral reef. And so handling those constraints we can use with something called a matroid. And the previous two problems were thinking about how you maximize your quality of service given a constrained number of resources. But the dual problem is how you can satisfy a certain quality of service constraint with as few resources as possible. So this is called the risk-sensitive coverage problem. And thinking about search and rescue, you want to make sure that you do an adequate job of searching the environment, but you want to use as few resources as possible. So in this environment, there's different levels of risk, and you have a large team of robots at your disposal, and you want to find a set of routes for those robots that successfully searches that graph while using as few resources as possible. And the common thread that ties these problems together is this notion of risky traversal, which we'll show later induces a diminishing returns structure. And so we're able to attack all three of these problems using very similar algorithms and a very similar approach. So let's talk a little bit more about these kind of routing problems and how we solve them. So most people, when they talk about routing problems, they're thinking about what their GPS does, which gets you the shortest route from point A to point B. And that problem is actually very easy, relatively speaking. These problems are different because here we're looking for the longest path from point A to point B, the one that gathers the most reward. And fundamentally, that's much, much harder to solve. So what you're looking at here is an example of trying to visit every city in Germany. And you can't really see it, but the red background there is actually a path that visits 15,000 cities that took 22 years to compute. And the problem is that this takes exponential growth. So if we were to add just a few more cities, you add a few more years to that computation time. So solving these problems exactly is not something that we can really do in practice. It's kind of a trophy whenever someone does and they put you on a high score list, but it's not something we do for real-world problems. So what a lot of people do are heuristic solutions, which typically are very fast, common sense, and they focus on tuning your algorithm for the specific problem at hand. But they don't provide you any guarantees. So we don't know whether or not we're within a factor of half, with almost optimal, or we might be off by a factor of 1,000. There's just no guarantees. And so you get a result, but you're not sure how good it is. So what we focus on in this talk is approximate solutions. And so here, our goal is to slow down a little bit and take a principled approach where we're able to provide guarantees that, yes, we're no worse than a factor of half of the optimal. So we know that we're doing relatively well compared to the best you could possibly hope to do. And the best part is that you do this in a relatively short amount of time. So this is something that you can actually run in an online setting where you're updating and reacting to information that you're gathering online. So some applications that have had a lot of work on these approximation algorithms are the orienteering problem. And in the orienteering problem, it's very similar to what we've been talking about before, where the goal is to find the longest path, or the most valuable path, given a budget constraint, where you only have a certain amount of distance or energy that you can expend. And there's been a lot of work in the last 50 years on this problem. There are approximate solutions, exact solutions, and even heuristics. But the point is that this is a problem we understand very well. But the key difference why we can't use it for our application is that there's no notion of, while there are a lot of variants for stochasticity and randomness, there's no notion of risky traversal. So when an orienteer goes down a path, it will visit all the nodes in that path. It's not going to fail as it travels. So we can't just apply this to the robotic situations that we've been talking about. Yeah?
I have a somewhat tangential question for you. Why is it called orienteering? I've always wondered this because it doesn't have anything to do with
so there's a challenge called the Orienteering challenge where you're given a list of coordinates and a map, and you have to basically take a picture of yourself at each of those coordinates. And they call that orienteering. And so there's sites you have to visit. You can't visit all of them in the amount of time that you have, so you have to choose which sites you're going to pick to get the biggest score.
So the constraint there is time?
Yeah, the constraint there is time.
It's a competition.
Yeah.
But the word orient has nothing to do with the problem. That's what I'm trying to...
I think it does because in that challenge you're trying to get yourself to a particular location.
And so lacking an instrument to get you
Yes, yeah, so it's like a compass and map.
Oh, I see.
Yeah, with the GPS the challenge is really simple.
I see.
But yeah, this is compass and map, and so there's dead reckoning involved that you have to keep track of where you are, and yeah, it's actually quite challenging.
But in your problems, finding your orientation has nothing to do with it. It's about getting to known points with known location and collecting the maximum reward.
Right. And the key difference from what's already been studied is that we have to deal with this now risky traversal model where we might fail as we go. And so how do we incorporate that? And so thinking more about teams, another big class of research is the probabilistic vehicle routing problem. So this is basically what UPS does or what Amazon does, where their goal is to deliver packages to all the customers, and they have a deadline that they're trying to satisfy. And because there's randomness, you can't guarantee that you'll do that, so you have some probability that you have to make sure that you'll meet the deadline by. So this has received a ton of work. This is just one of many, many variants of this problem. And while it does have a notion of deadline, there's typically a focus on heuristic solutions rather than exact solutions, and using higher fidelity models rather than approximations that we're able to actually reason about mathematically. And the key difference, again, there's no notion of risky traversal. Your UPS trucks don't simply die or get evaporated. They will visit all the sites. They might have a breakdown, but that's just a time delay, not actually losing your truck.
What is the probability here? Because this seems like it's...
So there's randomness in how long it takes you to travel. So traffic introduces this randomness, and so the time it takes you to reach your destination. Okay. Yeah. And then a third branch of related work is informative path planning. And this is more from the traditional robotics perspective, where we have a team of robots that are doing some monitoring task for the environment. So we're trying to track a school of fish or algae blooms or measure the temperature of a lake. And so the way you formulate this is that you use random variables in the information function. And the goal is to find a set of routes that maximizes the information you learn about these random variables. And this doesn't necessarily seem like the same as our problem, but it has the same fundamental structure of this diminishing returns property, which lets us solve these problems. And so this notion of submodularity, which we'll talk about a lot more in a second, is really what ties these problems together and why we're able to be inspired by a lot of the recent work in informative path planning. So just to go over the contributions, the main contribution is that we provide tools for routing in these risky environments. A lot of the existing work doesn't handle risky environments and doesn't think about what happens when your robots or vehicles fail catastrophically. And so that's something that in a robotic context is important to take into account. And the key idea, as I just said, is that we exploit this diminishing returns property that is apparent in a lot of these risky traversal problems. So the first step that we take is that we solve the single robot subproblem for how we route a single robot through a risky environment. And then we exploit this diminishing returns property to show how to use that single robot problem to solve the team surviving Orienteers problem, which is where you have a route or a set of paths you're trying to plan to maximize the expected number of sites serviced. And from there, we're able to give a couple of extensions by giving more details on when the problems have this submodularity or this diminishing returns. We can also handle heterogeneous teams that have different capabilities, and an online setting where all the robots are moving simultaneously through the environment. From there, we also are able to handle the matroid-constrained TSO problem. So here we're incorporating more constraints that enforce linear independence, such as how many robots you have available or where they can travel. And using the same ideas and the same tools, we can solve this apparently different problem. And again, we're able to use the same ideas and tools to handle the risk-sensitive coverage problem, where we're trying to satisfy that service level constraint with as few resources as possible. So this is what we'll be talking about today, but we also have a number of works in preparation that extend broader online settings. We also deal with more sophisticated algorithms, so the continuous greedy algorithm for matroid constraints and the cost-benefit greedy algorithm for risk-sensitive coverage problems. And finally, we also have extensions to broader categories of problems, such as when a person is trying to find a path through an unknown environment and the robots can help them out. Or if you have knapsack constraints, basically limitations on the sum of costs that you're able to deploy. But we won't really talk about those today. Okay, so this risky traversal model is really central to our approach, and so let's go through it in a bit of detail. What you're looking at here in this figure is a path that's planned by a robot. So there's a start node and a terminal node, and then there are edges that connect the dots that it's trying to visit. And so the robot starts out by trying to take an edge. And in this case, it successfully traverses the first edge, and so it'll visit the second node in the path. And then it tries again for the next edge, successfully takes it, and successfully visits the third node. But it fails when it tries to take the third edge in the path. And so because it failed once, it won't visit any of the remaining nodes in this path. And so this risky traversal model introduces this history dependence, or this path dependence, where the set of nodes visited depends on the path that we take to try to visit that node. And this history dependence is what really requires a new approach and a new set of tools, why we can't just apply all of the orienteering problem. Yeah.
And each path has an independent population?
Yes, yeah. So we assume independence, and that seems to be important. And that's primarily to make it so we can actually analyze these probability distributions. I'm sure that if you were to take this idea and use more black box approaches, it would still work really well. It's just analyzing it would become really, really difficult. Okay. Any more questions about this model? Because this is really central to our approach.
So you know all the information up front, all the probabilities, and they don't change.
Yeah, and that's actually one of the future works is what do you do when you don't know those probabilities? Because that'll change which paths appear to be feasible. And we'll talk about that more later. What we can not know is how much visiting each node is worth. And if you have an online setting, I'll talk about that in a sec, an online setting, then you can learn how much nodes are worth. Okay, so now let's talk about the team surviving Orienteers problem. This is the first of the problems we consider, and here your goal is to maximize the expected rewards given a fixed number of robots. So mathematically it looks like this. The maximization is a summation over the probabilities that at least one robot visits a particular node. So we sum over all of the nodes and look at the probability that at least one robot visits. And this is what has that diminishing return structure. Because as you send more and more robots out, that probability saturates to 1 and your returns basically go to 0. And now our constraints, the first one is saying that we care about our robots. So the probability that each robot successfully finishes its path has to be bigger than a user-specified threshold piece of S. So the idea, and this is central through our work, is that when you're sending out these robots, they cost you something. So I want the probability that it survives to be at least some number. It doesn't have to be super high, but realistically speaking, this could be 0.6 or 0.8. The point is that this is relatively close to 1 rather than relatively close to 0. Then the last two constraints are just saying that we start at a particular node and end at a particular node. And remember, our goal here is not to solve this exactly, but to develop a relatively fast algorithm which has provable approximation guarantees. So let's look at this problem in a little more detail. So what really makes this problem hard? And I've kind of already said this, but first off, we're looking for maximum weight paths, which is a hard problem, but one that's been studied for a long time. We're also looking for a set of paths, which again is one that's been studied for a long time, and there are a lot of tools for that general problem. But what makes none of those tools apply is that we have this nonlinear and history-dependent objective function. So if we expand out that probability that we just had in our objective, it ends up with a summation with a difference with a product with a difference with a product. So if you try to use a logarithm to turn this into a nice linear form, it doesn't work. And there really aren't standard tools that gets this into a nice linear form we know how to solve. So this is really the central difficulty for this problem that we have to address. And the good news is that this objective is submodular. So what does submodularity mean? It means it's a formalization of a very intuitive diminishing returns property that we interact with every day. So if you think about going to the gym, your gains of going to the gym decreases the more often you go because you basically picked all the low-hanging fruit. At least that's my experience. Formally, given the set function, what the math says is that the returns for adding a new item to a smaller set is bigger than adding it to a larger set. We have this diminishing returns. Now, why do we care? Well, for an example first. So if you think about tossing a bunch of coins, as you increase the number of coins that you toss, the probability that you get at least one heads increases less and less. And so that's what this figure is showing. It's just as you increase the number of coins you toss, very quickly your returns are diminishing. And the reason that we care about submodularity is that instead of looking for all of the items at once, if we're trying to pick 10 items, looking for all the items at once is really hard. But instead, we can just look for the next best item and iteratively build a set of 10 items to solve. And we don't lose too much. So in the 70s, it was shown that you're guaranteed to get at least around 63% of the optimum by using what we call this greedy approach. So just to give a visual example, if we're trying to cover all the nodes in this graph, the optimal solution looks like this flywheel. But if you were to take a greedy solution, the first step you take might be wrong. And so you won't hit optimal, but you're not too far off, even though you didn't consider all the paths at once. And so this is kind of why we like the greedy algorithm, because it has this guarantee. And not only that, that you can't actually get stronger guarantees in general in polynomial time. So the greedy algorithm is not just fast and effective, but it's the most effective for its speed. So now we can go back to our TSO problem and reformulate it in terms of submodular function optimization. So our set is the set of all the paths in our graph that are safe enough. And what we're trying to do is to maximize f, which is the expected number of nodes that we visit with at least one robot, subject to a constraint on the number of paths we're allowed to pick, because we only have one path per robot that we can plan. This is a canonical way of formulating a submodular optimization problem. And so we can solve the much simpler greedy subproblem, where instead of looking for all of the paths at once, we just look for them one at a time. And so now what we're looking for is a single path that maximizes, and this is the expected number of new nodes visited by this robot. And unfortunately, because of risky traversal, this greedy problem is still NP hard and actually really hard. So we need a way to solve this. So let's expand out this problem a little more. What we're doing is we're looking for an argmax over the sum of basically probability of first visits. So it's probability this robot visits the node and no previous robots have visited that node. If you think about it, that's exactly what the discrete derivative should be. That's your incremental gains. And the difficulty is that this probability that the robot we're currently planning for visits a node is history dependent, as we mentioned earlier. And so this is why we can't just use an orienteering problem to solve this. So how do we get around it? We know that this probability is within a small region because we have a lower bound on the survival constraint and an upper bound of 1, or we can even make it tighter by solving a shortest path problem. So we have this nice bound that this quantity lives in, and so we can plan optimistically, where we replace the actual visit probabilities by an upper bound. And what we were able to show in our paper is that now this is history dependent, so we can use an orienteering problem. And not only that, is that if we solve the orienteering problem reasonably well, then we get reasonably close to a good solution for this history-dependent problem. So if you think about your survival probabilities, remember those are close to 1. And if you solve the orienteering problem relatively well, lambda is close to 1. And so you don't lose much at all for taking this optimistic approach. And now that we have a handle on the greedy subproblem, we can go back and put together the whole algorithm. So at each iteration, we form our orienteering problem appropriately to deal with this risky traversal. We use a logarithmic transformation to get into an additive form. And then we find each path by using an approximate orienteering problem solver. And we add that path to our set and repeat. This is just the greedy algorithm specific to the TSO problem. And our main result is that the approximation ratio is 1 minus e to the negative p sub s over lambda. So again, if p sub s over lambda is close to 1, then this is recovering that 63% guarantee that we had hoped for. So in practice, this works relatively well. So in theory, the bound gets worse as your survival constraints go close to 0. But what this figure is showing is that over synthetic data, we actually keep the same performance as our survival constraints get looser. And so a single robot is achieving about 60% of the upper bound, which isn't the optimal, but it's close to the optimal. And as we add more and more robots, we do progressively better. So the blue line on top is showing that with 5 robots, we're basically recovering all of the reward we could hope to in this problem. And this problem had about 65 nodes. And that dip that you see right around 0.8 is because that's where the problem hasn't been solved yet, because it's constrained enough that the robots can't just go out and visit all the nodes. And so we would need to give more, or allocate more robots to solve this problem exactly. And we were also able to use that pinwheel graph earlier that you saw to compute the exact optimal, because there's a lot of symmetry and we're able to visually and quickly verify what the optimal is. And on that graph, what you see is that our greedy routine almost recovers the optimal. So we give up a little bit, but our upper bound is also really close to the optimal. So this approach seems to work really well on the problems that we can check it with the optimum. And the nice thing about our approach is that by abstracting away to just solving an orienteering problem, it's easy to consider many variants. So for example, we can consider variants where the nodes are weighted by different amounts, and the way we do that is that we just solve a weighted version of the orienteering problem. We could also consider a variant where instead of getting rewards for visiting nodes, you get rewards for crossing edges. So in scientific missions, a lot of times the journey is what's important, not the destination. And there's an arc orienteering problem that we can use to solve instead of using the node orienteering problem. We can also consider functions of multiple node visits. So information is an example where you get a lot of reward for taking one sensor measurement, but you also get reward for taking a second and a third and a fourth. And so we can incorporate that easily into our framework. And all that we require is that that gain diminishes the more times you observe the same thing, which makes sense. Heterogeneous teams is also fairly easy to incorporate into our setup. And the way that we do this is that we solve an orienteering problem for each type of robot, and then pick the best one in our solution.
What differentiates the robot types in this?
So an example would be if you have rovers versus UAVs. They'll have different graphs that they can travel over and different risks. You could also have cameras that are really cheap or really small UAVs versus cameras that are really huge. That'd be another way, where your reward function is different for each type of robot. And the key algorithm feature, as I said, is that it's very easy to incorporate these orienteering problem variants. And so we can also incorporate heuristic solutions versus approximate solutions. There's just a lot of flexibility in our approach. We've also considered online update cases of the TSO problem. And so first, we could think about what happens if the node rewards are unknown. So we've assumed so far that we know how much each node is worth, but in a lot of settings we don't. And so the way that we handle this, one way would be to send robots out one at a time, and they report back their observations so that later robots can incorporate those observations into their plan. And this actually fits into a framework proposed by Krauss and Gestrin, which is the Adaptive Submodular Maximization Framework. And without doing any extra work, we can use their results along with our previous results and show that the expected reward of this kind of a strategy is at least 1 minus e to the negative ps over lambda of any policy, any way of responding to this type of information, which is a really strong statement. Another way of thinking about online updates is when all the robots move out simultaneously. So this would be where time is really important and you want to finish the mission as quickly as possible, but you want to adapt to make sure that you're minimizing the risk that you're exposing your fleet to. So the way that we do this is that if too many robots fail early on, we force their paths to be more conservative. Or if fewer robots fail early on, then we can allow them to be more aggressive. And so we solve this optimization problem to adjust the survival probability threshold to keep it consistent with our initial estimate. And it's not surprising that if you plot a histogram of what happens when you do or don't use this online controller, the distribution is much tighter when you use the online approach than when you don't. Makes a lot of sense. You probably didn't need to run the histogram to guess that, but it's good to see the data. So that wraps up the team surviving orienteering problem. Now let's talk about the matroid constraints. So remember that matroids are capturing linear independence for these set functions in these problems. And in this application where we have environmental monitoring, this could mean that we can only send a few robots through particular sensitive regions, or we only have a limited number of different types of sensors that we're allowed to deploy. So these types of constraints where you have subsets of paths that you can only pick a handful from are one of the most common matroids that we deal with. So formally speaking, well, you can think about the cardinality constraint that we talked about for the TSO as being a matroid. But formally speaking, it's defined by this tuple of all the items in your ground set plus a family of independent sets, which must satisfy two properties. First, they have to be downward closed. So if you have an independent set, all of the subsets of that independent set are also independent. And second, it has to satisfy an exchange property, which is crucial, which says that if you have two independent sets that aren't the same size, then you can always swap an element between the two to create new independent sets. Now, in practice, what is a matroid? So if we think about robotics problems, there's actually a lot of applications. So think about that aid delivery scenario where we have a bunch of sites that need resources, but we're limited in how many resources we have available to deploy. And so that limitation on resources is actually a matroid constraint, saying that you can only deploy 2 units of food or 2 units of medicine or 2 units of water. Another application are the regional traffic constraints that we've already talked about. Or we could have risk constraints. So thinking about the search and rescue scenario, we have some areas that are extremely risky. And so we might be able to relax the per robot risk constraint so that we can send them into this very risky setting. But then we would enforce a constraint that says overall our exposure can't be too much. So we can only pick one super risky path, but we can have a couple of moderate paths and many safe paths. This is also a way of formulating a matroid for robotics problems. You could also think about launch or runway constraints where in deploying you have limitations on who can go when. And nested cardinality constraints where you could take any of the applications earlier and nest them within each other. So the point is that matroids are very expressive and can cover a lot of applications that we see in robotics pretty often. And the way that we solve it is that we can use the greedy algorithm. So that exchange property allows us to analyze how a greedy algorithm performs with these matroid constraints. So the only difference from our approach to the TSO is that now we search over independent items. So instead of searching over all of the next best items, we're only allowed to search over next best items that satisfy the independence constraint, which makes sense. If you've already used all your fancy sensors, you can't pick another one. You have to pick one of the cheap ones. And so the way that we do this is using graph decomposition. We start off by linearizing the problem as before. So it sets up a big orienteering problem. And then we decompose the graph into subgraphs which have the property that each of the paths in these subgraphs is independent. And we describe how to do this more in our paper. And then you solve an orienteering problem for each of the subgraphs. And then you pick the best of these problems. Sorry, this isn't in the handout. You pick the best of these problems and add that solution to the set. And then what we're able to show is that, actually using some work that Professor Vondrak published, we're able to show that our constant factor guarantee is P sub s over P sub s plus lambda. So thinking in the setting where P sub s is close to 1 and lambda is close to 1, this recovers about a half approximation for the algorithm. And a big question for a while was whether or not this was as good as you could do, and it turns out it's not. There's a more sophisticated continuous greedy algorithm, which we were able to extend to our setting, and that recovers the 1 minus e to the negative P sub s over lambda guarantee in the limit as you become continuous. And so essentially by doing a bit more work, we don't lose any of our theoretical guarantees by taking on these matroid constraints, which is pretty incredible.
What is the notion of continuity here? Where do you take the limit?
Yeah, so essentially what happens is that you solve a greedy problem 1 over delta steps, and delta is your discretization variable. So as delta goes to 0...
Time or space?
So you keep track of a distribution on essentially which items you've already selected in your previous steps, and then each time you pick an item again, you increment that probability by delta. So it's kind of in probability, if that makes sense. Yeah.
Okay.
Yeah, and the real expert on this is Professor Vondrak, because it's his algorithm.
So you're setting the items are the paths?
Yes.
So the constraint is like on top of the possible paths?
Right, right. So this isn't a path constraint. This is saying which sets of paths are you allowed to pick. Yeah.
But it could also be the different types of robots.
Right, right.
Represented
right. Yeah, yeah. More questions? Okay. So to show off on the kind of applications that we can use this for, we modeled a complex environmental monitoring task in the Coral Triangle region, which is out by Indonesia. And we have constraints on the conditional value at risk for our whole team, traffic throughput through regions, and the number of each sensor type available. And what you're looking at in this figure, the heat map is corresponding to piracy incidents and kind of inferring the risk of threat from piracy. That's actually a big issue in this region. And the boxes are showing different ecologically similar areas within this Coral Triangle environment. And the little X's are actual sites that we would want to visit with our robots. And so we have different types of robots that are better at measuring different ecologies, and we want to find a set of paths for this group. And so what you're looking at here now is basically the performance as a function of the team size. And the reason why there's a gap from the upper bound is because it's harder to come up with a tight upper bound for the matroid constraints, because you have to reason about, well, what is allowed with the constraint. And the key point to take away from this figure is that we're showing both the reward when we solve the orienteering problem well with a mixed integer program solver, but also when we solve it with the variable neighbor heuristic, which is much, much faster. And what you see is that they get basically the same reward. So this is just to re-emphasize the point that I made earlier about the extensibility of our algorithm, how we can very quickly interchange different orienteering problem solvers to recover the properties of those solvers. So in this case, having very, very fast solutions to this problem. We've also done a study on the computation time for the matroid team surviving Orienteers problem. And this is something that you can solve on commercial or standard hardware. So a desktop PC can handle this no problem. And so what we did is we looked at synthetic graphs with throughput constraints on different node clusters within the graph. And so the clusters are all about 15 to 20 nodes, and we solved the orienteering problems almost exactly. So we have a 5% tolerance on that solution. And what you're looking at in this figure is that even for a problem with 600 nodes and 100 robots, it only takes about 40 seconds to solve. So we can solve these very quickly, and part of the reason for that is that there's a lot of room for optimization in terms of skipping problems that you don't need to solve because nothing's changed. And so the point is that we can solve these really well, and it scales very well with both the number of subproblems you're solving and the number of robots in the graph. So now let's talk about the last problem, which is the risk-sensitive coverage problem. So remember, this is for when you have a search and rescue scenario where you want to ensure a certain quality of service, where you're visiting nodes or regions with particular probabilities that are specified, and you want to use as few resources as possible when you do this. And so mathematically, it looks like this. We have a minimization problem now, where we're minimizing the team size or the amount of resources that we're using, subject to the constraints that we're familiar with, where we have the per robot survival constraint and the routing constraints. And now we have this additional constraint, which says that each node has to be visited with some minimum probability. And these are specified by the user. this PV of j. And so the way that we attack this is, again, using submodular function optimization. So we define this function g of x, which is the constraint function. And what this is saying is that we're going to add up the amount of constraint that we've satisfied for each node. We don't get bonus for overachieving, but up until we've hit the constraint, we get to add up the probability of visiting. And the key property of this function is that if a set satisfies the constraints, then the function saturates. So if we evaluate the function with all possible paths in the graph, then it's the same as at that set that satisfies the constraints. And so now we can reformulate the risk-sensitive coverage problem as a submodular optimization problem where we want to find the smallest set that satisfies the saturation constraint. And this is called the submodular set covered problem, and the way we approach it is to greedily select paths. And what we mean by greedy here is that we pick paths or items that maximize the amount of constraints satisfied. Because if you think about it, that's maximizing their greedy usefulness. And so mathematically, this is almost identical to the team surviving Orienteers problem, where we're maximizing the expected number of nodes visited. The only difference is that now we have this min operator that takes a little bit of nuance, but fundamentally doesn't change the problem. Unfortunately, the guarantees are a lot weaker for this setting. So what you're looking at here is what we would call a bicriteria guarantee. The first inequality is saying how far we are from the smallest set for solving a problem. And the second guarantee is saying how close we are to exactly solving the problem. And so let's look at this in a little more detail. In the first guarantee, the first term is the penalty we pay for not exactly solving that history-dependent path planning problem. Inside the second term, we have a logarithm of this ratio. Now, this ratio is problem-dependent because what it says is that if the value of the first robot to the last robot is very, very different, this ratio will be close to infinity, and this guarantee basically becomes useless. But if you think about what that means that the last robot you sent out basically covered none of your constraints. And so you've almost exactly solved the problem without that robot. And so that's how we get this kind of two-way guarantee that says you can either barely solve the problem with a really tight guarantee or very accurately solve the problem and have a pretty loose guarantee. So we tried this out on a search and rescue scenario where we used storm data from NOAA and a published model for how risk kind of influences robots flying through a storm. And the goal is to visit each of these nodes with probability of 95%. So that's fairly strict. And what you're looking at in this figure is how our approximation ratio changes as a function of the constraints that we satisfy. And you see that spike at the end. And what that's saying is that it takes 36 robots to satisfy 100% of the constraints, and our guarantee is 20 or 19. So all this guarantee can say is that it takes at least 1.5 robots to solve all the constraints. Very, very loose. But if you back off just a little bit, so satisfy 99.7% of the constraints, it only takes 27 robots, and your ratio is now 6.75. So this is a much more reasonable solution set. And that's part of the value of this approach is that the operator can now say, well, I didn't really mean 95%. 94.7% is plenty. So let's use that and get a strong guarantee. And if you back off even farther, then a team of 13 robots, that's almost a third of the original full solution, you get a ratio of 4. So it gives you a really wide variety of guarantees that you can pick from to pick the set that you actually care about. So this ratio, you take the number of robots it took to solve the problem, divided by the ratio, and that gives you 3. And it says that it takes at least 3 robots to satisfy 80% of the constraints.
Now, these are plots resulting from your theorem? Or
these are from simulations. Yeah, so this is for the setting that we talked about right here. Where I solved this problem, and remember the guarantees are problem dependent, so depending on the specific solution that I got, I can give these guarantees. One of the weaknesses of this problem, or one of the difficulties of this problem, is that you can't really come up with guarantees separate from your problem solution, because it depends on that relative utility of the first and last path that you select.
What did you label? Theorem 2 and what?
Yes, sorry. Theorem 2 is the theorem from our paper, and the rounded guarantee is just using common sense to say that if it takes 3 robots to satisfy 80% of the constraints, it takes at least 3 robots to satisfy 100%. So you enforce basically monotonicity and round to integers.
So what's the association of this plot with theorem 2?
Yeah, why is it not monotonically?
Sorry?
Why is it not monotonically increasing if it's a theorem?
Well, these are simulation results, right?
Yeah, these are simulation results.
Why does it relate to theorem 2?
Yeah, so, well, it's because if you look at the theorem, it depends on your solution. So that's what this term is here. It's saying the actual solution you got from your first path versus the actual solution you got from your last path.
You plug it into this.
So you have to plug it into the theorem, and then you get the guarantees. And that's what I was saying before. The guarantees are weaker because they depend on your solution. They can't, without seeing the problem, I can't give you this guarantee. And you can actually, people have proven that it's inapproximable within constant factors. You have to depend on your actual solution.
So it's a theorem plus a solution in terms of that, correct? Right. I mean, the theorem.
Right. Yeah. So. Right. Yeah. This plot probably isn't the best figure.
I'm sure I understand. You could just simulate, run many simulations, just how many robots you need, right? Why do you need a theorem at all?
Well, because to actually figure out the best way to allocate your resources is really, really difficult. So I don't know what the minimum resources are to satisfy your problem constraints. So that's what the theorem is saying, is that, you know, if you're able to relax your problem constraints a little bit, maybe you picked a super hard problem just because you chose 95% instead of 94.7%, and that requires more robots to satisfy. So the theorem is saying that we're able to kind of balance how closely you satisfy the specified problem with how strong of a guarantee or lower bound you want on the minimum number of robots to satisfy that problem. Does that make sense? Okay. Yeah. All right, so another way of looking at the effectiveness of our algorithm is using a very symmetric problem. We're able to cast it as an integer program, and then we can get the exact solution. And so what you're looking at in this figure is that our greedy solution is no more than a third larger than the exact solution for these settings. So even though the guarantees might be like saying that we're within a factor of 2 or 3 or 4 or 20, in practice, we're getting very, very close to the optimum. And remember, we're doing this with a lot less effort and much more generality than we're able to compute these optimums for. All right, so that wraps up kind of the main core of my dissertation work. The contribution is that we've developed these mathematical tools for handling risky traversal and risky routing problems. And so first in that is that we identify these conditions for diminishing returns structure. So we've identified a broad category of problems where we have this diminishing returns structure with this risky traversal model, and settings where we have the diminishing or heterogeneous teams and multi-visit rewards and things like that. So there's really a broad category that has this structure. We've also been able to show how to approximate the greedy subproblem by using standard established approaches. And so by using this optimism principle where we replace the true probabilities by an upper bound, we don't lose too much. And that proof is what lets us use all of these existing results for solving the subproblem. And finally, we're able to approximate these broad class of risky routing problems using this approach. So it's not just that we're solving a specific problem for a specific application, but we're solving the TSO problem, the matroid TSO problem, and the risk-sensitive coverage problem using the same basic tool set. So this is a really generalizable approach for solving a broad class of real-world robotics problems. But it's not complete, so there's still a lot of work that we could do. One of the big questions is whether or not we can eliminate our dependence on this survival probability constraint. Because while it's reasonable to say that we care about our robots, we might not care that much. And so our results tend to get weaker as P sub s goes to 0, but that's not necessarily because the problem is hard, that's just because of the way that we approximate the single robot subproblem. There's probably ways that we can get around this. Second is, how should we handle unknown edge weights? So as Professor Vondrak asked, what happens when we don't know the survival probabilities? And one of the key problems is you might discover that a path is actually a lot safer than you thought, and now your ground set of items changed, because what used to be infeasible is now feasible. So that's a fundamental issue with our approach that needs to be extended in order to handle how to learn these edge weights. And the third question is whether or not we can go even more general, instead of thinking about paths, to think about policies. So now the set of policies is still a finite set. We still have a limited number of paths we can pick given all of the observations you make. And so if you can optimize to solve the greedy subproblem over this much, much larger set, you'll get a much richer set of robotics problems and that are more amenable to online optimization. And you could probably also incorporate the unknown edge weights. And the fourth question, and this is kind of a holy grail in robotics explorations right now, is how do you do parallel online exploration in an unknown environment? So this figure up here is showing a classic, you have a robot in a room that it doesn't know anything about, and what happens, how do you solve the problem where you want all the robots to quickly explore this building, dealing with risk, dealing with uncertainty, and do it with guarantees? And that's something that I think we have some building blocks for in this dissertation, but would take a lot more work to get to actually solving that problem. And the fifth question that I'm personally really interested in is how do robots interact with people when doing these missions? So a lot of times the robots aren't working alone. The firefighter example, the robots are working along with people, or if they're going into a building to make sure the building's safe or free of people when it's burning down, again, you want to work with people. And one of the problems that we've looked at is, can we identify safe paths for the human to take through this dangerous environment? And I think that's a really interesting set of problems that hasn't really been touched in the current literature. So thank you very much. Thank you each of you for being here. You've had an impact on my research, whether you knew it or not. I've read several of your papers and had good mentorship from all of you. And thank you particularly, Professor Pavone, for encouraging me to push through the first results into the second and third and fourth and fifth results. Really learned a lot about exhausting a problem from you. And a huge thank you to my wife for her support throughout this process, even when the results were lacking. And a thank you to our son for giving me a really good motivation for getting all this done now. And thank you to my parents for their encouraging me to go for the PhD, even though I wasn't sure about it. It's been a good ride. And a big thanks to the ASL folks for making this a lot more fun than it would have been if I was just sitting in a cubicle by myself. So thank you all for being here.
Yeah. Even though I screwed up last time and did not get the form signed, so make sure.
Oh, all right.
So we'll have, this is the open period for questions. Are there any questions from the audience? Yes?
Regarding the graph that you plotted, the theorem 2.
Oh, yeah.
So you said that the bound was solution dependent, right?
Right.
So did you run multiple solutions and just take the best ratio you could get from that?
I tried not to. I mean, I did run multiple solutions because sometimes there are mistakes with the way I had generated things, but no, this isn't cherry-picked. I mean, if it was cherry-picked, I would have gotten a better answer than 20. Yeah.
Any more questions?
Probably a simple question, but at the very beginning you said that some of the constraints include the beginning and end node.
Right.
So it seems like for these type of problems, the end node would usually be the beginning node too, like you want the next one to come back. Yeah. But if you, for some reason, wanted them to end in a different location, would there be a case, like I could foresee there being cases where you wouldn't find any feasible paths, like maybe your probability guarantees of success?
Yeah,
like
so one of our results is showing that you can quickly identify if there's no feasible paths. Okay. Because if you think about it, that's saying there's no way of getting from point A to point B beyond a certain distance. So you solve a shortest path problem and, oh, I found a way, so it's feasible. So that's really easy to identify. And whether or not you have the rooted variant or you allow it to end at any node, that's really a variant of the orienteering problem. So those constraints are what we implemented, but that's not necessary or inherent to the problem. Yeah.
Any more questions? Okay, well, let's thank Stefan again. And then reconvene the closed part of it. The defense.
How are you doing?
My Google Calendar was
Thanks for coming.
That was so good.